I'm very glad that so many of you found their way to my session, especially given the competition. I saw that Brian Getz is on the other stage. I say this now because I now know it's too late that you can escape, so you have to stay here. I'm from Hamburg, Germany, and I work as a consultant for smaller businesses, and I try to help them implementing or talking them out of using machine learning for their business. And the title, of course, it's very provocative, and every time in the title you see a question mark, it's always that the answer is no, unfortunately. So if you're afraid that your job is going to be taken by machine learning, it's not, so don't worry. And the final slide will be a slide I stole from the keynote. I will tell you right now, but you will forget that you as a software developer might add machine learning to your skill set, and that's all. So, well, now maybe I killed the cliffhanger, but I had to do this. Anyway, okay, let's get started. I worked out a scenario. I've used it several times, but is there anyone in the audience who already saw this example? No one, that's great. Okay, good. Let's imagine we are in the car insurance business, and we are the CTOs. We are in charge of running that car insurance business, but we are different from other car insurance businesses because our rates are actually based on actual accidents. That means if you have a lot of accidents, you pay a high rate, and if you have no accidents, very low rate. But the challenge is, of course, how do you know if a prospective, like a new customer, will that customer have a lot of accidents or few? Because once you've insured someone, you still can change the rate, but only as an afterthought, after the fact. So this is what I ask you, or I asked myself to build. I'm the CTO and the developer at the same time. I ask us to build a system like this, where you can punch in a few basic informations about someone who wants insurance. The first one is top speed of a car that you want to insure. The second one is the age of the driver. And the third one is how many miles per year do you drive. And this is all in miles. That means 100 miles per hour is around 160 kilometers. So this is a real application. And you can check it. It's running TensorFlow.js in the background. It uses a machine learning model. I will show you the model later. And it tells me that's a low risk. That's actually my data. So no, wait, it's not my data. I hope this doesn't change it. I'm sweating a little bit, still low risk. Thank God. So if you manipulate this here, I don't know, 77, and I recalculate it, it gives you a high risk, for example. So if you punch in someone who's a little bit younger, and I tried this before because sometimes it's a little bit astonishing, then you get a medium risk. So we want an application like this. You add some data, you get a prediction. Is this customer going to be good or bad? That's our challenge. Oops, not right. Yeah. How would you solve this? So as a software developer, I'm used to solving things by writing code. And this code here on the right side is typically what comes out of the job of a software developer. And oops, pressed the wrong button, I'm sorry. Fixed. And often, this is based on requirements, and these requirements are sometimes written down, sometimes not, but they're always somewhere, as a mental model, as a concept. And these requirements come from analyzing or thinking about a domain. And the domain in our case, obviously, is car insurances, or how many accidents people actually have. And then you might have a person, or at least a role, that analyzes that domain or thinks about it, writes down some requirements, and out comes a program. Anyone of you ever having worked in an environment like this? Okay. Who has not ever done anything like this? You? Okay, but I just saw one hand. So this seems to be a very common setup for a software developer. Obviously, this talk is not about this setup, but about another setup. But first, let's see how I came up with some rules that describe if someone is a good customer or someone is a bad customer. So first rule that I came up with, or a set of rules. If someone is younger than 25 and has a high-speed car, that's probably not good for an insurance company, because that person might end up having a lot of accidents, and then also bad accidents. And this is in Python, but it could be in Java. I mean, it's so simple. So red means high risk. And then if someone is younger than 25 and doesn't drive that much, it's still in the middle, so that's medium risk. The next rule that I had is if someone is pretty old, unfortunately, older people tend to have more accidents, also high risk. And if people drive a lot, and this is not that much, this is around, let me guess, 50,000 kilometers per year, not that much, the risk goes up. And if you drive a little bit more, then just occasionally, you're in the medium risk. And if none of these rules apply, your risk is green. This is, of course, not real business logic, but it could be. I've written stuff like that many, many times. Anyone who has never written business logic that's similar to this? No one? Or who has written software like this? No, wait. Who has not written software like this but doesn't dare to show up their hands? Still no hands, okay. Silly question. So anyway, I'm not saying this is bad all by itself, but it has some things that I never thought about until a few years ago when I turned a machine learning person from being a software developer. And one thing is, how good is this? I've never thought about it. Is this better than guessing? Do you think it's much better than who thinks this is much better than just guessing? A lot of hands. It's not. So it's not much better than guessing. But it doesn't look like. I mean, I will show you evidence, and then you will believe me. And then, are the rules correct? Some of the rules maybe you're frowned upon, like if someone is older than 75, does that automatically mean you're a bad driver? And especially for the green area? I don't know. That would also mean maybe we are missing some rules. There might be both too many and too few rules. And then, again, how would we even know? Do we have a measure for that? Sometimes, I mean, if you're like in a really organized company, you might have, but often I had no measures at all. So a different approach to the whole problem would be almost like an inversion of the whole thing. And this is a quote from someone, and I'm reading out. Machine learning gives you a second way to talk to computers. The old way was giving the computer explicit instructions, whereas the new way is to give examples instead. And these examples are the data. So given we have already some customers and collected some knowledge about these people, why not use that data? And that's the idea of machine learning. So this is something I drew from a database, just a few sample data. This describes one existing customer. So this is the data that I know, that I have, that I know for sure it's good. So someone with a car that's pretty slow, about my age, doesn't drive too much, that's in the green area. So this is someone that's a good customer. Next one, also good customer. This one, not so good, pretty young, drives quite a bit, car a little bit too fast, bad customer. And this one here is in the middle, and then this one is also a good one. And these things are things that I know. It's not that I derived it from something, but just look in my database and see, did the person have a lot of accidents? This only works if you have data in your database. If you don't, it doesn't work. Now, are we actually able to make predictions based on these data points? And what I did as a visual experiment is that I plotted two of these dimensions, namely age on this dimension and max speed on that in this diagram. And each of these points here is a customer that I have. And the color represents if it's a good customer or a bad customer. Again, this is green here. Some people told me I should use blue because some people have a hard time telling green from red. Hopefully, my explanation helps. So this is all green. Oops. Was that me? Not sure if it's issue with this thing here. Or is it me? No.
Can you see it in the front?
No. Oh, wait. It was me. I'm very sorry. I again pressed the wrong button on this thing, I think. We have to wait for a second, because I know it takes a second on this until this recovers. But it's my fault. It will recover. I see it in the front, so no worries. There you go. Oh, no. This time it wasn't me. I'm not sure what's wrong here. Not touch it again. I have a different adapter. Maybe I'll take another one. I'm very sorry for the technical issues.
Seems to be coming. So wait a second. Finds it and then goes away.
Maybe I'll take this one.
Yeah.
It usually works. Looks better. The other one was a little bit jiggering.
Yeah.
Good. I see it, so bear with me. It will work. It will be great. Aha! Who lost faith in me already? Just try to calibrate how honest you are with me. So, not quite sure where I left off. I'm very careful with this thing here now. So this is a plot of all, or a sample of all my customers. And for example, this customer here, age 30, cars around 110, a mediocre driver. That means yellow represents mediocre customer, and these green ones good, and these red ones not so good, and these red ones also not so good. And the question that I'm having to you is would this data view be helpful in predicting for a new customer? And I again put down my data here. I did this when I was still 47, now I'm 48. This is the data, 47, 100 miles per hour. And the way I would do it is around here is 47, around here is 100. I would draw a new point here. Hopefully you see the data pointer here. And then I would say, this is so close to a lot of green dots that I would say this new customer could also be a good customer. And this is just a sanity check to see, is the data actually, is it useful to make predictions? And I think if you look at it for a while, you can even see clusters like down here. You see, we don't have a lot of customers that are a little bit older, but if you have, they're not so good drivers actually. And you see if someone is a little bit older, not like very young, and has a very fast car, it's not such a good driver. And you also see that in this area here, we don't have any data. And you also see that the data is not 100% clean because we don't have a 10-year-old driver, I hope. I see this now. But this is what happened. So I would say yes, this would be the first sanity check to see, does it make sense to go on with a data-based approach? And I would say yes. I would be a little bit worried because those are not a lot of samples, but we can still try it. And if I was to draw in areas in this thing, it's a little bit different, the plot, but it doesn't matter. I would say all these parts here, they would be good, like good customers, not so good customers, not so good, in the middle and also in the middle. And these lines here, they're called decision boundaries because they separate different categories of drivers. That's just a word I will use repeatedly, so I'm introducing it here. And this I did by hand, obviously. But the question is, would it be possible to compute these decision boundaries? I don't want to always draw this myself. I could hire some people, and they would do it for me manually, but I'm not so sure if that's a good idea. So the question is, can we do this somehow? And obviously the answer is yes, otherwise talk would be pointless. And the idea is to turn this around a little bit. So in this case, the model, which we had on the left side when we were talking about actually programming, is what comes out of the whole process. So we stick in data that's coming from a database. It should be cleaned. In my case, it wasn't quite clean. 10-year-old, probably not. Interesting. And then we put this into a tabular form. You saw a tabular form a little bit earlier. And then we decide which of those columns that we have are the ones that we are trying to predict, because this is a deliberate decision, and which other columns are we going to use to predict that one. And in our case, this column that we were trying to predict is the group or the category of the new customer, good, bad, not so good, or in the middle. And these inputs here would be speed, age, or maximum speed, age, and miles per year. And these are all things that you typically have to think about it for some time, and it's not at all obvious. But in our case, I made it really simple to just for the sake of simplicity. Okay, so we turned this around, and this is the thing that comes out, which is actually completely the other way around. Now, let's have a look at decision boundaries plotted by the rules that I showed you earlier. And it's not, if you look at this for the first time, again, it's a little bit different. The data points that you see, it's not easy to see what it means, but these again are decision boundaries. This, and then this, and this. And they also separate the different areas of what is a good driver and a bad driver. That means all this green area here is where my rules would have predicted good driver. And then this area is where my handwritten business rules would have predicted not so good driver. You see, this is 75, and everyone who is older than 75, not such a good driver. And you see all these drivers around here, because you don't suddenly turn into a bad driver, but you, at a certain age you get a bit worse. They are obviously misclassified. And this area here doesn't cover this at all. The whole green block in the middle, not good. This one here barely touches any data points at all. So it's not so good. How many of the data points do you think are correctly classified? So to make that really clear, this one is not correctly classified because it's a yellow one and the prediction is red. But this one is correctly classified because it's red in red. And this one is also correct, 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 wrong, 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 wrong. How many of them are correctly classified? What do you think? Just shout something. 20. So I heard something between 20, 40, and 50. How good is guessing? 33, exactly. Someone said 50, which would be correct if you only had two different categories, but 33 is guessing. So if you were worse than guessing, that would be, it's extremely hard to be worse than guessing. So you need to spend a lot of time doing that. And then you could turn it around and then you would be good. So this actually is 43. So the people who said 40 were pretty good, but 10% better than guessing, not good. Who would have thought that this is so bad? I mean, really. A few of them, okay. I would not have thought that. I mean, I know it now, but at the time I didn't know it. I thought it was sort of okayish. And that questions part of my professional life, to be honest. Not good, but not, I'm like, turned a better person, no worries. So a machine could learn to write those rules, and maybe in a better way. And it works, trust me, this is a real thing. It works by, or one way it works is by building up decision trees. I know there's a typo, but other than the typo, this is real stuff generated from a machine learning model. And you will see the code that created this. And you can see on the top, there's one decision that would be like if then. And the question would be, if the speed is smaller than 146, then I will predict yellow. That's how you read it. And these other informations are about the algorithm trying to find out where to put the splits. But on the else part, we check if the speed is lower than 196. Then next check, then we check the age, and so on and so on. And I'm zooming out to give you an idea how this is going to end. If you were writing this in if rules, and I'm just trying to make sure that you understand what you're seeing here, how many levels of nesting would you have, or would this require to put it down? Okay, I'm doing it with you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 levels of nesting. Has anyone ever in their professional life written any code that has 14 levels of nesting? You did that. You touched it. We need to talk later. Maybe I buy you beer. I think you're not on video, so no one will see your face. So maybe you want to stay anonymous. But surprisingly, this maybe is a little bit too detailed, but this is about the level of detail that you need to actually make a good prediction for this. No one wants to maintain this, of course. Let's see how the code for this looks like. This is code in a library called scikit-learn. And scikit-learn is, I wouldn't say this in the data science conference because the war would break out if I said this, but I can say it here. This is the most popular classic machine learning library. And there's also the R community. Anyone here from the R community? So I'm safe, because that is a community that would challenge this, and for good reason. But let's have a look. This is Python, and I'm just importing a class, decision tree classifier. You saw a decision tree. This is a constructor call. Well, it's missing the new, but other than that, it looks like Java. It also misses the type annotation here in line 2, because there are no type annotation in that sense in Python. But it doesn't matter. Then I'm calling a method on the classifier. I stick in the training data, which is the 3 columns of age, speed, and miles. And I also put in what is to be predicted. And this is the group. And I'm training this whole thing. And then once that is done, oops, sorry, I can use that classifier. Typically in between, you also save it to disk, you load it later, you deploy it into production, but this is left out in this case. You can use it to make a prediction on previously, well, maybe unknown data. And then you get that prediction, story is over. And I'm showing you this code because the whole concept thing is much more complex than that code. Obviously, this code is very simple. But I'm also showing you this, and I'm also linking to the notebook, where you can try this out yourself. And as I'm a little bit brave today, I will click on this thing to show you how, as a machine learning person, you would write something called software. And I'm saying this because the approach is very different from actually writing real software, because you often do this kind of work in so-called notebooks, which are a REPL on steroids. So you punch in some data at a certain point, you execute it out of sequence, and you can mix it with text. So I'm executing this thing, and what you execute is, yes, please, is one cell at a time. And you just execute that snippet of code, and then you change the state of the notebook, and then you could execute the next thing here, downloading the data, reading it in, printing it, making some analysis. So that's the real code, and it's not too complex, but you will see, if you look at it from the perspective of a software developer, you would say that's barely a script. But this is like almost all the people in that data science or machine learning community at least sketch their ideas. This runs on a Google service called Colab. And Google, I'm not a fanboy of Google, but Google gives you for free high-performance GPUs, which is pretty surprising. There you see it. It's a K80 GPU, high-performance scientific GPU, and then you will need that for neural networks. But that is just a side note. So let's return to the slides. And you will find exactly this code in that notebook if you want to play with it later. And it's just a link, no installation, just click on it, just play with it. It actually works. So let's see. This is the result of this thing. And again, you probably still remember how to read this. The background is the prediction of that model. And the foreground, it just stays the same. This is just our data. You see, it's much more detailed, but you also see it's still blocky. It looks like a lot of blocks. This is a property of decision tree-based approaches. So our handwritten rules were of the same nature, but this blockiness actually doesn't reflect the real world. The real world, so to say, expressed in decision boundaries is much more smooth. So this is not the best model you can have, but it's still 70% of accuracy. That means 70% of those dots are predicted correctly, which is quite a bit. So we were going from 43, and we would have been able to bring this up a little bit to 70 by generating those rules. Well, or learning those rules. But maybe I'm going back one slide. Now, here's something suspicious. It's 70% accuracy on unknown data. Yes, because machine learning is all about something that you don't know. It's all about generalization. So this is our model here, and you want to learn concepts from data. This is the data that you know, to apply it to data that you don't know. So actually, you don't care too much for data that you know, because if I was giving you the assignment, write me some piece of code that can perfectly 100% reproduce the data I have in the database, what would you do? Is it? Yeah, query the database. And then you have, or I don't know, if you want to make it more complex, create a hash map or something. It doesn't make any sense. So what you really want is you want to train on data that you know, and you want to apply it to data that you don't know. And if that works well, that's called good generalization or generalization. So the problem with that is that you don't know what you don't know. So how can you potentially test how well your stuff works on data you've never seen? And this could also be interesting if you were writing your rules by hand. And the trick here is to split the data that you have, like your whole database, into two parts. One part, typically the bigger one, you use to train your model, or you use to do analysis, and then the smaller part you use to test the result. Is it a good result or not? And this is to simulate unknown data. If you use it, it's a pretty simple trick, but if you've never seen it, it could be interesting. So typically, or very often, what you see is overfitting, or something called overfitting, namely that the accuracy, the scores on the data that you know, are much higher than the scores on the data you don't know. And the process of bringing this test score up is called regularization. And what also happens if you bring the test score up, you often bring down the training score as well, for reasons that are beyond this talk. But this will happen to you. So if you bring test score up to, say, 74%, you will also bring your training score down to that. Depending on what kind of strategy you're using, you need to do different things. For something we didn't go into, so I'll skip that. For decision trees, what you can do is you reduce the depth or you use more than one decision tree and average over the outcomes of all the decision trees. And for something called support vector machines, there's other stuff. And support vector machines used to be the hot shit before neural networks came in. And neural networks, just by the number of things that you have to do, you see they are the most powerful, but also the most complex thing in that respect. Now, once we've done that, so I thought overfitting using neural networks, we get this result, which, I don't know, do you know Baba Papa here? Anyone? Yes, you do. This is Baba Mama, right? Do you see her? And you see that hair thing on, and I see the necklace here. So anyway, but as Baba Mama is very smooth and nice, so is our model. I mean, it's not all blocky. It has weaknesses, and we'll come to that. But it's the best model I could come up with, and it's about 80% accuracy on data that it has not seen so far. So, all well. Let's look at the code. And we are not going into detail here. This is written in TensorFlow using a high-level API, which will become the main API of TensorFlow in the next version. And I plotted it here because you will see that this part, this fitting of the model, is very similar to the scikit-learn and the prediction. It's the same method name, but the setup of the whole thing, and this is a tiny neural network. This is tiny. This is almost nothing. It's much more lengthy, and you see a lot of regularization in between. And this is the real model that really does that prediction. But you will see that you need to understand a lot of stuff until you can apply it. But then you might be able to get good results out of it. This is TensorFlow. This is the, without any question, most common library to create neural networks. The second one would be PyTorch. A lot of academics like that, but if you're not in academia, you probably will use TensorFlow. And the model that you saw, or better to say, the application that you saw earlier, this one here, it uses a TensorFlow model that you can also bring to JavaScript and then let it run in the browser, which is surprising. But we are not there yet, unfortunately. Because let's look at something weird. If your car is really fast and you're really young, I don't know, 27, what do you expect? Look at this. Anyone, I mean, other than that I obviously failed on the task, why would that be? Yes, no samples in that area. Let's have a look. Because it's not that easy. That's why well, this is how the decision boundaries look like if we zoom out. This area here still is what you saw before. And this actually is a modified plot because it looked a little bit strange before I modified it, but anyway. And all this area, not a single sample, nothing. And still the model is very happy to make good predictions here. That's all yellow here. And this is all red. Why is that red? Why is that? And this is because the model has no clue about what to predict here, because it has never seen any data. And that is obviously a big weakness, because we all expected if it goes up, that's just logical. It should know that if you have a really fast car, that's really, really dangerous. But of course, this thing has no knowledge about the world. So what to do about it? First of all, be aware. And if you are asked to make predictions in that extended area, at least give a warning to someone who asked for it or refuse to make a prediction. Then sometimes it's possible to identify a score that you always get when the model has no idea. In our case, it's yellow. And yes, that's what I said. If you can, try to get more data. That's the problem here. We just don't have data in that area, but you will never get data for someone with a car that goes 1,000 miles per hour. So this doesn't always help. And then if you give a wrong prediction, ask the user who uses the model, please give us the right prediction here, and you can retrain. But one thing that's most powerful is adding real likelihoods to scores, or asking the model, how confident are you? And there's this thing called TensorFlow probability, which does this for you. I just screenshotted this first page because I thought that's good enough. And instead of putting in just data points as features or inputs or labels, what you're trying to predict, you feed in distributions of data. And this is out of my comfort zone because I was never good at that stuff, but this is the basic idea. And then what you also get out of it is also distribution, where it tells you, for one, how sure am I and what do I expect? So after we've gone through this first example, let's make this a little bit broader to leave you for the beers a little bit later. And the question is, what works good with this? This is just an example that I made up. It's based on something that's real, but it's not really real. So where could you apply this? I said it doesn't always work, but what are the rules? So the rules, and those are actually my rules, it's not like written in stone, is this sort of stuff works well when the problem is hard to specify. And something that's not hard to specify is legal regulations, for example. If you're younger than 17 in Germany, you must not drive. No need to have a machine learning model. But if the question is a little bit more vague, who's a good customer, then it might be a good thing. You have to have a lot of examples. In this case, I would even question that the number of examples we had were good enough. And you did see it in the outcome. This was 1,500 samples that I was drawing from a database. And with 3 categories, that means around 500 examples for a category, and a lot of spots were missing. Probably not good enough. Most important thing, solving the problem can tolerate some error or at least uncertainty. If you think about self-driving cars, which are all the hype, and we are trusting machines to make the decisions, are we actually cool with them making errors, or how big would the error rate be? In this case, well, not so bad, but if it's military stuff or cars, then it must be clear what they're feeding in and what you get out. If you just don't know, if you just say, we will give it to the AI, it will not work. And then also something that strikes me pretty often, it is perfect to replace a gut feeling. Maybe you have a boss who says, I have that gut feeling that the customer wants this and that. It's perfect to replace it with something based on data. I know you don't speak German probably, but our Minister of Transportation said that he has the gut feeling that the speed limits on German Autobahn, they won't save someone. And then if you look at the data to justify the gut feeling, you will find that having speed limits will limit the amount of accidents to half. So if you want to fight someone like this, it's pretty simple to do it with data. This is something I stole from Andrew Ning. And he's very famous, and he has made up a list of things that work today. So it's not something that will work, but something that does work. Among that, translation from one sentence to another. And it's based on machine learning, what you can do with Google, for example. Preventive maintenance or predictive maintenance. Something, you say, will something fail or not? What else do we have? A loan application. That's tricky, because often if you have a loan application, people have the right to know why they have been refused. And this often is a hard thing in machine learning, but it might work. And there's more stuff, but let's go with it. So, as I said, I'm broadening and get more broader now, because we're coming out of the rabbit hole now. And the question is this stuff the kind of machine learning that we just saw, where we put in data and get something out, is that all there is? That kind of machine learning is called supervised machine learning. There are other types, and other types are, for example, unsupervised machine learning, where we don't give the right answers. And there's reinforcement learning, which is pretty hot at the moment, where we say an agent can make its experiment in an environment. And this stuff up here, intrinsic motivated agents, it's science. So we don't do that. Okay, but this also exists, so that you know that the stuff that actually works best, which is this, supervised learning, what we are looking at, is not all there is. But this is what works best. So what does not work? I'm pretty sure you know, but I have a hard time fighting the hype about all this. And the thing to know is there is no general API. There's no conscious robot that can learn by itself, and there's no autonomous thing about it. And it's also not that this robot on the right side is just the more smart version of me. It's not like we create an AI and then it can do things. And I asked myself, why do we even think that is a thing? And I found this, better say Gene Kogan found this. And you can see, new neighbor device learns by doing. And then the important part is, this new device will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. I think by the typeface, you will see that this is not brand new, right? Who has any idea? I mean, my point is, because if something really nice happens, the press wants to talk about it. When has this been published? What do you think? If someone knows, don't spoil it, please.
1947.
No, it's later. That would be cool. Maybe they had it at that time and they hid it from us. No, it's 1958 and by the New York Times. So not like the Bild-Zeitung in Germany, not like Boulevard, but actually serious press. And they thought it was a thing, it will do it. So my point here is we should not let us be fooled by the press. So how do you actually use machine learning projects? So maybe you found out, okay, it works. You know that there's limitations. What do? One thing that's really very different from software engineering is that often machine learning are experiments that can fail. That means it's not like in building software where you eventually get it done or you redesign it and it will work. In machine learning, it's often that it doesn't work at all, never. For example, in our case, we have 1,500 data points. We will never have a decent model. And you will find out on the way. And that's really tricky. Because sometimes the next step you're building it into an application depends on the success of this step. Because, well, if it doesn't work, you don't want to build the software. And that's why it often feels like more like product owner work or project manager or business analytics work. But some part of that, once that experimental phase is done, is still close to engineering, which makes it really strange because now all of a sudden you can again work in an environment of a software developer. And then you could also be part of an agile team. So the basic thing is, machine learning projects have uncertainty over both time frame and outcomes. So you have no idea how long it might take for you to actually get to decent results, and you don't even know if you will get decent results. If you tell this to your manager, he will say, oh no, he will not say, just give you a year, just do it. This doesn't work. That makes it also pretty tricky if you're serious about machine learning. And then there's two approaches. And I think it depends on what school you're coming from. There's the control approach, and some people have really interesting ideas. So they say, you don't say, after this comes that, but you model a probability distribution for the outcome of something, and then depending on that outcome, that this project plan goes in this or that direction. Well, there's very smart people who believe in this, like this person, but I've seen, what's the name, the Microsoft thing with the Gantt charts, Microsoft project. Have you ever used that? It's already so complex that I don't believe in it. So another approach could be that and this is something I've seen working. This actually does work if you explain people why they should do it. So work in very short time boxes. That might mean You try it for a day, and then at the end of the day, you present results to someone, to the team, maybe in a stand-up, and then be honest and open about what's your feeling about it, does it work or not, and then based on that, you decide if you go on or not. That's a little bit like Agile, but a little bit harder, because now at each of these very small iterations, it could mean you're not going to go on. And this is hard for me as a software developer. That's pretty hard. So, does machine learning kill business logic? And I promised you I stole a slide, and this means we are coming to the end here. Stole the slide by Friedman, who did the keynote this morning. I would say machine learning will become a standard software engineering technique. And that, from my perspective, means we should all, I'm not saying you should do this, it's just a recommendation. I recommend that you learn a little bit of that to understand where machine learning might actually be the better choice instead of writing business rules or something. Okay, wrapping it up. So we saw that machine learning can learn from existing data, and it should generalize to unknown data. If it doesn't, there's no point. Sometimes, but only in certain cases, it can be an alternative to business logic. There's no common knowledge about the world. And I hear this so often that I cannot repeat this enough. This doesn't exist. There's no general knowledge about the world in machine learning. The head of SAP, or better say AI of SAP, also had this experience, and he keeps also telling that no strong AI means no general knowledge. You can't just let your problem be solved by AI, and machine learning is an engineering effort, and a big one. And at the last part here, we also saw that the approach of machine learning might be at odds with classic and also with agile approaches or projects. I think we're out of time. If you stick around for beer later at the, I don't know where it is, if you have questions or input for me on that, because it's also something that I'm stating as a problem, especially the last part, and not having a good solution, I'm happy to talk to you. And here, clapping from the other room. Do you have time for question? One question? 2 minutes? Is there a question? Yes?
I thought you said that you failed.
Yes.
In this sample with one particular. But did you? I mean, you got a pretty good model, didn't you?
So the question is, did I really fail? And I would say, in a sense, yes. At least the thing that I delivered, so my calculator, I wouldn't use it because it doesn't actually catch right now the areas where it should make a prediction. But apart from that, maybe the model wasn't that bad. But I would not bring this into production. That's why I said I failed. But I think if I applied all the other things in the other slides, I might as well be okay. But I actually need more data. Yeah. So this is a very, so the question is, how much data do you need to make it work properly? And this is extremely hard to say because it depends on the certainty that you need to have at the end. And it also, well, I could define this as okay, and then it's nice. But the rule of thumb is, for something like this, 5,000 samples. But this is just a rule of thumb. For something much more complicated like images, you might as well need millions of samples. There's an anecdote when Google trained their self-driving cars to recognize house numbers. They had, I think, a few billion labeled samples, so a few billion pictures of house numbers, and some poor people actually wrote the real number next to it, and they trained their model on it. And that's easily a few million samples. So it depends. But, well, this might just as well be good enough, just like you said. Maybe you would be satisfied. You wouldn't fire me, but it depends. Okay, with that, thank you very much, and see you at the rest of the conference. Bye-bye.